So this work, I want to talk to you some work I did about 25 years ago, and then more recent work that kind of completed it. The first bit of work was funded by NATO. I don't actually know if I'm allowed to talk about it here in Russia, but we'll assume the statute of limitations had passed. When we finished the project, we had to send in a report. We had a number of results, and we actually didn't have space for all of them, so we didn't include this result in our report because we didn't think anybody would be interested in it. It turned out it's actually my most cited result, and it's cited by a lot of people that are outside of computer science or mathematics. And so before I talk about the results, I just thought I'd talk about some of the places in the real world where this comes up. So we've got Epidemiological Networks. This comes from the American Journal of Public Health from 2007. They talk about using transmission network analysis to complement routine TB contact analysis. And that's a graph of a tuberculosis outbreak in Oklahoma in 2002. And it's patients that have been infected in their contacts. And one of the things that epidemiologists are starting to study quite a bit now is the fact that that these networks are inhomogeneous. Some people know a lot more people and contact a lot more people than other people, and so the degrees of the vertices are different, and that means that when they're trying to figure out how to attack an outbreak, they should take that into account. And we're going to talk about that too. So this is the Internet Mapping Project. It still exists. This was in this was in May 3rd, 1999 that they took this snapshot of internet sites, and the coloring is by top-level domain name. And of course, again, interested in routing through the internet or preventing problems because of DOS attacks. So again, you're thinking about the connectivity structure of the network. This is a picture of the interactions between proteins in a cancerous rat cell. So most of these clusters are related to the cancer. And in order to attack the cancer, they want to understand what the structure of the clusters is. This is just a social network, like the picture. This is something you may not have seen before. Good friend and colleague of mine, Bill Cook, together with David Applegate, Bill Bixby, and Vashak Fatal, they have the fastest code for the traveling salesman problem. Okay, they solve million city problems. And in solving the traveling salesman problem, I mean, the actual difficulty really is to showing they have the optimal solution, right? Usually, actually finding the solution is not hard as showing that it's the optimal solution. But in finding the optimal solution, what you typically do is you find the lowest cost, not single tour that goes through all the vertices, but two-factor or true regular graph, if you like, that goes through all the vertices, which has minimum cost, which can be done efficiently. And then you try to patch that up to get a Hamilton cycle, right? You just take these two cycles and you do this kind of swap that Colin Cooper talked about in his talk. You go from AB and CD to AC and BD, right? And you get one less cycle. And Colin was looking to make triangles. We're looking to make one Hamiltonian cycle, right? And so he's interested in what's going on with two cycles. He wants to understand how to patch them together. And then he was looking at the Euclidean problem. So say we take n random points in the unit square, okay? And we find the lowest cost two-factor when the weights on the edges are their Euclidean distance. Okay? And he observed that there seems to always be a linear-sized cycle. Okay, there's a component, if you like, in this. And he asked if that was true. And so that's an open problem. I don't think it's an easy open problem because there's a lot of dependency in that model. But it's another example of this coming up in practice. Okay. And of course, we've had talk about percolations. We take some graph, often the lattice, and then we just keep each edge with some probability p. Right? And we want to know what the components that we get are. If it's an infinite lattice, we're asking if, I'm going to move this over. We're asking if we have a component of infinite size, and if it's a finite lattice, we're asking if we have a component which has a positive fraction of the vertices. Okay. And again, that's a question that we're going to be interested in. Okay. And then there's been lots of talks that have focused on this. I put the one I put first because it's one, again, that comes from the real world, similar than the others. Okay? So it's a question that arises a lot. And why do we want to think about these random models? Well, one thing you can hope is that the random model is like the real world network. Right? And then you can say, okay, well, by working with my algorithm on the random model, I can see how well it would be doing in the real world network. But you're also doing well if your random model is not like the real world network. Because then you can say, how does a real world network differ from my random model? What's the structure that differentiates it from the random model? And then you can take advantage of that structure. Right? The others used to say if the graph is random, then the problem's easy, and if it's not random, we'll take advantage of that. Right? And we've seen an example of that already in a sense, because for a uniformly random two-factor, okay. Sorry. For uniformly random two-factor, as Lutz said, the size of the largest component is not concentrated. Okay? For every epsilon between 0 and 1, the probability of a component size at least epsilon n is bigger than 0 and less than 1. Okay? So when Bill asked me what's going on with the Euclidean two-factor, then we're actually saying that this random model is different from the uniform random model, and we can ask why it's different, and maybe that will be useful in developing an algorithm to solve the Euclidean TSP more quickly. Okay. So you want to ask whether or not there's a giant component in a random graph, and what determines this? Well, of course, the more edges you have, the more likely it is for there to be a giant component. But the other thing that matters is the degree distribution. So of course degree distributions differ in these real world networks. I put up 3 there. So this is sort of the network in the brain between nerve cells. And so it's moved there to show you that it's Erdős-Rényi. Okay? So that it's Poisson distribution, so the proportion of vertices of degree k dies off like e to the minus k log k. In fact, in the brain, it's not a 0-1 connection. It's not that there's a connection or not. There's a weight on the connection. There's some amount of connection between each cell. And here you put a threshold. and said I'm going to say there is an edge if the connection is bigger than that threshold, and I'm going to say there's no edge if it's below the threshold. This is Facebook friends, and it sort of looks like a power law with a number of vertices of degree k. The proportion is like k to the minus alpha for some alpha. Except we see two things here. It drops to 0 at 5,000, and also it's a little bit low for numbers like that are less than 20. Right? So why is that? Well, it's because Facebook doesn't allow you to have any more than 5,000 friends. Right? And it's also because if you've got less than 20 friends, Facebook sends messages to all your friends saying, help Bruce get friends. Right? And that's why you have that little dip. So again, this is an example of where you can look at the random model, you can compare the empirical to the random, and by looking at the factor of difference, you can deduce, something strange is going on at those 2 points. It's a simple example, but it illustrates the point. Okay, and then of course you can have a fairly simple constant. Every vertex has the same degree. And of course, as we've seen, and we've had lots of talk about, I think I'll slip this side, what the degree distribution is will affect whether or not a giant component exists. Right? So, again, what does it mean to say G has a giant component? It means there exists epsilon greater than 0 such that probability G has a component of size greater than or equal to epsilon n goes to 1 as the size of the graph goes to infinity. And G has no giant component that means for all epsilon greater than 0 probability G has a component of size, I'll put epsilon, sorry. Well, n is the number of vertices. And then, of course, you can have some behavior that's in the middle, like with these random 2 factors where neither of those 2 things occurs. Okay? And so we're interested in whether or not there is a giant component, and we want to fix a degree sequence and say for this given degree sequence, I'm going to choose a graph uniformly over from this degree sequence and ask whether or not it has a giant component. So we're talking about simple graphs here. We're not in the configuration model. We're not allowing loops, and we're not allowing multiple edges. Okay? And so my degree sequence then is d1, d2, up to dn. Right? And we're taking a uniformly random graph subject to vertex I having degree I. Okay? And we'll call that graph GD. And we can assume these are all greater than or equal to 1. A vertex of degree 0, just throw it out. Right? It doesn't have any effect on what's going on. And we also can assume, just to make the exposition easier, that it's non-decreasing because it's the same answer for any permutation of the degree sequence. You just permutate the labels on the vertices as well. Okay? And so now I'm going to start off by trying to answer that question. And I'll start with an answer from 1995. Okay, so what's your heuristic argument? You want to start with a vertex, and you want to explore the component that contains that vertex. So you start off, you look at what the degree of V is, and you have that many open edges to explore. And you explore one of them. You find out what the vertex of the W is, and now you have some more open edges to explore. And what's the change in the number of open edges? Well, you get dw minus 1 edges, but you lost one edge out of V. So the change is the degree of w minus 2. And what's the probability that you pick w? Well, you'd expect it to be proportional to the degree. Okay? So the probability you pick w should be degree of w over the sum of the degrees. Right? So what's your expected change in the number of open edges? It's the sum over all the vertices of the degree times the degree minus 2. Right? And then divided by the number of edges, twice the number of edges, total degree. Right? So it's a branching process. It should go to infinity if it's positive. Right? And it should die off if it's negative. And of course, as Remco said, in his talk, you don't just do this once, you do it a bunch of times. It'll die off a few times, but eventually, if this is positive, you'd expect to grow up, blow up into a big component. Okay? So how do you make this a proof? Okay? Well, the first thing is right? We just said it's intuitive that we probably pick W as dW. Well, we need to actually show that we probably pick W is almost proportional anyway to dW. And the second thing we need to show is the expected change remains constant, remains positive throughout the process. And the third thing we need to show is that the number of open edges tracks the expected number of open edges. And if we can do those three things, we got a proof. Okay? And so that's what Mike Malloy and I did back in 1995. And we were interested in specific applications, so we had quite a few conditions on them that we didn't worry about. One of them being a bound on the upper maximum degree of at most n to the 8th. We showed that as long as this sum was greater than epsilon n, there is a giant component. And if the sum is less than epsilon n, then there is no giant component. Okay? And so how do we do these three things? Well, this here we went to the configuration model, which you've heard people talk about, right? Which is where you allow loops and multiple edges. And in that model, the probability that you pick W is precisely dW over the sum of the degrees. Okay? But we're not in the configuration model. But the point is, under these technical conditions, well, first of all, if you're in the configuration model and you get a simple graph, conditional on getting a simple graph, no loops and multiple edges, it's a uniformly random simple graph. So we are in the configured configuration model, or the conditioned configuration model. And the point is that under the technical conditions, the probability your graph is simple is not too small. It's a little O1, but not too small. So if you can prove the probability things are bad in the configuration model is really, really small, it's still really small under this condition model. So we just translated from the configuration model here. And why is this true? Well, that was just true, because we imposed those conditions. But again, as we'll see, the fact that we imposed an upper bound on the degree helps in keeping the expected change positive. And here again, what's going on here? Again, the technical conditions ensured this, but What's your change in each step? Your change in each step is the degree minus 2. Right? So you're doing a process where your change in each step, as long as the change in each step is small, the random variable is going to be concentrated around its expected value. Right? So precisely the technical conditions, but in particular, again, very important that you bound the degree, allows you to show that the expected value and the real value are going to be close together. The variable is concentrated. Okay. So that's what we did back then. So now we want to think about high degree vertices, because we've seen in these power law degree models, we can have vertices high degree. So how can we prove this result? Why can't we prove this result for graphs with high degree vertices? The main reason we can't prove it for graphs with high degree vertices is because it's false. Okay? Think about this graph here. Think about a graph where degree 1 equals 1, degree 2 equals 1, degree k cubed equals 1, and degree k cubed plus 1 equals k squared. Right? Then what's the sum of d times d minus 2? I'm getting 1 times minus 1 here, 1 times minus 1 here, 1 times minus 1 here. Actually, I'm going to make this k squared plus 2. K to the 4th plus 2k squared here. Right? And the sum is k to the 4th plus minus k cubed plus 2k squared, which is way bigger than the number of vertices k cubed plus 1. Okay? So here we start off with the expected change being hugely positive, but what happens? Well, for a while we pick some matching edges, but then suddenly we pick a vertex that's incident to the high degree vertex, right? And now this goes away. Now this one goes away, and all of a sudden we're at minus k squared, k cubed, right? So it's what Remco referred to as a depletion of degrees, right? We just lose the positive guy, and now it's minus 1, and we're just going to go down to 0, and every time we're just going to stay at 0. This is the only graph on that degree sequence, right? 1 star with k squared plus 2 leaves, and then a bunch of matching edges. I mean, up to, of course, the labeling of the vertices. Okay, so that we can't prove it because it's not the right answer, but suppose that we could figure out what the right answer is, we'd still have some problems about proving what the right theorem was. And what theorem would we have, problems would we had? Well, if you've got high degrees, the probability of being simple isn't so big anymore. Now the probability of being simple can be really, really, really small in the configuration model, so we can't just translate the result from the configuration model. And also, it's hard to prove concentration results because your values at each step can change by quite a bit, right? Remember, the degree minus 2 is how much the value of the variable we're tracking can change at each step. Okay, so if we got to figure out what the right answer is, and then we have to figure out how to deal with these two problems. Okay, so let's try and do that. So how much time do I have?
You have 15 minutes more.
Okay. Good. So again, we got a degree sequence. We're choosing a uniform graph with that degree sequence. D is non-decreasing, all to be positives, and we want to know whether or not we have a giant component. Okay, so in order to explain what the real answer is, we need 4 definitions. Okay. And maybe I'll write them down here. Sorry. So for reasons that will become clear in a moment, we're going to want to know the sum of the degrees which are not 2, which I'll call M. And we're going to want we're going to want it to be well behaved. And simplifying slightly what's on the side, we want that M goes to infinity as the number of vertices goes to infinity. Okay? And then that's a sort of a technical detail we'll discuss in a minute. The important definitions are JD is the sum, is a minimum I such that the sum from 1 to I of di minus 2 is greater than 0. And RD is the sum from JD to N of I equals JD to N of DI. Okay? So previously, we were taking the sum of d to di minus 2 to JD, and we got to 0, and then we saw what the sum of the rest d times d minus 2 was. But now, instead of for the rest taking d times d minus 2, we're just taking the degree. Okay? So, and why does that make sense? If I can find what I've done with a flipper. Oh, did I put it down there? Yeah, okay. Thanks. Well, certainly this number is smaller than the old number we were looking at. Okay? It's smaller because in the old number we're taking d minus 2, and at JD the degree is at least 3 because we've gone positive. For the guys at degree 1 we get a minus 1, for the guys at degree 2 we get a 0, and for the guys at degree 3 we start to go positive again. So if we're going greater than 0 we have to be at degree 3, so if instead of counting du we count du times du minus t, we're getting more. Okay? But here's the key point. As it stays positive for at least RD steps. Okay? Because what happens as we pick degree out, the sum of the squares go down. What is the worst degrees to pick out to make the sum of the squares go down the most? It's the ones at the highest degree. Right? And so if we only pick guys above JD, that's the worst that can happen. And then still we've picked out like half of that. We still have that RD is at least what is before, half of what it was before, and so the expected change will still be positive. So this gives us a lower bound on how long it takes until we've depleted the degree and we start to have a negative expected change. But also it more or less gives us an upper bound because those are the vertices we expect to pick. If we're picking vertices proportional to their degree, we're going to get the high degree vertices first. Right? So these guys are the ones that are going to be first, and once we picked up degree RD, we're going to be negative. So this tells us approximately how many edges we're going to explore until our expected change goes negative. Okay? So here are the two theorems. We look at RD, not the sum of d times d minus 2, and we compare it not to n, but we compare it to m, to the sum of the degrees which are not 2. Okay? And if it's at least epsilon m, then GD will have a giant component. And if it's little o of m, then GD has no giant component. This is joint work with Felix Juice, who's now at Birmingham, Guillaume Fernand-Loubet, who's in Barcelona, Dieter Rottenbach at Ulm. Okay. So what's different here is we've been talking about the number of edges rather than the number of vertices. And we haven't been talking about all the edges. We've been talking only about the edges for vertices that don't have degree 2. Right? So why do we do that? Okay? Because we can throw the vertices of degree 2 away. Right? We can build this multigraph, and then we can put the vertices of degree 2 in. Right? And the vertices of degree 2, essentially, we can take any subdivision of the edges. Right? That's not quite true. For this loop, we needed to have 2 edge. If we're going to make it simple, we needed to have 2 red guys here, 2 degree 2 guys here. And for this 2 parallel edges, one of them has to have a degree 2 vertex on it. Otherwise, we'd have parallel edges in the final graph. But that's not too strong a conditioning. And essentially, the proportion of degree 2 vertices that drop into any edge or drop into any component is proportional to the number of edges that component has. So if in this graph we have a component with a high proportion of the edges, that in the final graph we have a graph with a high proportion of the vertices. And it's not, yeah. So that's, and so our argument that tells us intuitively that we're going to get a high proportion of the edges, and also note that RD is the same in this graph. Because when we threw away the vertex degree 2, for vertex degree 2, d times d minus 2 is 0. Right? So the same answer for this and this, we get the same value of RD and the same value of M. So that's the result. Now why do we have to insist that M goes to infinity with the number of vertices? What about badly behaved graphs where M does not go? Well, what I can tell you about badly behaved graphs is they're badly behaved. Okay? Remember, one example is if M is 0. If everything has degree 2, then we don't have a giant component. We don't not have a giant component. The size of the giant component works. And that's the same answer. Same answer for any graph which is not well behaved. Okay? Because you'll have, with a good reasonable probability greater than 0, you'll have a constant fraction of the vertices in a random 2-factor. Okay? So we actually know what's going on with the badly behaved vertices. It's just not the same thing. So we actually know what's going on for all of the degree distributions. Okay? Yeah, and so those are the results. We're down to
9 minutes.
9? Okay, good. So those are the results, and that's the intuition behind it. RD tracks how many edges you get to throw in before the expected change goes down to 0. And now let me tell you just a few more details of the proof. Okay? Or a few details of the proof, or an intuition of the proof. We've already seen some of it, right? We suppress the degree 2 vertices and we look at the multigraph that we get. Right? And we want to know whether we've got a component in there which has an epsilon proportion of the edges. So we go to edges, not vertices. Okay? And we're using the combinatorial switching argument to obtain bounds on edge probabilities in this multigraph. And it's exactly the combinatorial switching argument that Colin talked about and that I showed you when you make a Hamilton cycle from a 2-factor. Okay, you compare, we'll see a bit more about that, but you use this switching argument to bound the probabilities, because one of the things you need, what are the 3 things you need to do? You need to do these 3 things, right? So the first thing you need to do is to show that the probability you pick W is almost proportional to its degree, and you do that using this switching argument. Okay. So what do you do in the subcritical case? You just take all those high degree vertices and you don't row the component containing V, you grow the union of the components containing V and the high degree vertices. Okay? And you say their union is going to be small. Okay? With a good probability. So if their union is small, then obviously the one containing V is small and the one containing all those big guys is small. So so that's, and you also prove, you show that the drift becomes more and more negative over time, right? And that's just a deterministic fact. That's not, it's likely that will happen. And if you think about our example, right, with the matching edge and the star, right, if you pick a matching edge, then the drift stays high. But as soon as you don't pick a matching edge, as soon as the thing gets bigger than size 3, then you've made it more negative, okay? And so it's the same kind of thing here. If the component doesn't die out, then your drift has to be getting more negative. So you've dealt with problem 2. Well, like in this case, you wanted it to stay negative. And also you had to get rid of the high degree vertices so you could show it was concentrated. But you did get rid of the high degree vertices because you put them all at the beginning. They're not going to be picked. They're all in the initial set. Any vertex W that you pick has degree less than RD, and it's not hard to see that's going to be less than, well, root n. Okay? So what happens when a giant component, when you're in the supercritical case? Well, what you do is you look at the high degree vertices, and this means it's higher than root m over log m. And you just expose the union of the components containing those high degree vertices. And there's two things that can happen. Okay? Either the sum of the sizes of all those components which contain a high degree vertice is linear, or it's not. Okay? And if it's linear, then using the switching arguments, you can show that it's just one component and you have a linear sized component. And if it's not linear, then you can show when you throw away its vertices, the supercriticality conditions still hold. And now you can apply the supercritical when you have low degrees. So now you can again deal with the concentration, and also that allows you to show the expectation won't change very much throughout the process either. So we sort of combine then the branching process, the probabilistic arguments, with this combinatorial swapping argument. I call it switching. And by combining those two things, we can see exactly what's going on for all degree sequences. Okay? And maybe just a last word about how do we prove things about, maybe Colin showed you this. I wasn't here on Monday. But if he did, I'll just remind you. How do we show things about switching? Right? Here I got one family A of graphs and another family B. And what am I doing? I'm switching. I'm taking a graph here. I'm going A, B, C, D. And over here I've got exactly the same graph, except I go A, C, B, D. So I get this graph and that graph. So I'm switching, and I can build a bipartite graph here. And I can join one graph here to graph there if I get them by switching. Okay? And so suppose I have a bound here. Which way did I do it? So everybody here has degree greater than or equal to D. And everybody here has degree less than or equal to delta. Let me make this delta. Right? Then what can I say about the number of edges? Right? I can say it's greater than or equal to A times delta. And I can say it's less than or equal to delta times B. And that allows me to conclude that A is less than or equal to delta over delta times B. Right? So using this switching argument, and we have to use it in a recursive, iterative, kind of complicated way, but that's the basis, just using the switching to bound the probability of different families of graphs. Okay? So my focus, right, is to prove the most general result I can, which means you're not going to get the strongest result you can. Right? It also means it's easier to talk about. But so here we just said where the threshold was. We might be able to figure out what the size of the largest component is. We might be able to go that far. And that's an open question. Okay, thank you.